reapplied the same filter to remove that frequency. So finally, the two parameters that need optimization are the phase that we need to add to the signal in order to counteract the oscillation, and the amplitude or the gain of the filter. So, okay, here again you can see the two parameters. So actually these are, so again I tested this new implementation on the same operating condition of the machine, where again we have the first stage where we excite the load, and then a small pause, and the controller action. And here you can see the results. Again, the controller is effectively reducing the oscillation of the payload, and here again you can recognize the three phases. So here is just a fixed sinusoid to excite the payload, a small pause, and the controller action. And expressing the effectiveness of the controller in terms of damping ratio increase, you can see a similar results as before, so 4.5 times. As a last step, I also applied the same filter-based controller strategy for the payload to the independent metering block, in order to show that this methodology is actually applicable to a different control system, a different hydraulic control system. And so here you can see a very similar plot to the previous slide. The only difference here is that I'm also plotting the outer boom meter out command, where we can see now that actually when the command is negative, which corresponds to the lowering of the outer boom, which corresponds to an overrunning loads, we are actually, or actually the controller is actually controlling this meter out edge in order to keep the pressure level of the other chamber to a level to avoid cavitation. So to conclude this presentation, the summary and my main contributions are that I introduced a general formulation, especially for the cost function and the auto-tuning procedure for the application of this method on the oscillation reduction for the machine. And I also demonstrated how the application of such controller can also give benefits in terms of energy efficiency of the machine. And in the second part, I introduced this novel frequency-based approach, and I gave two different versions, one based on the FFT and one based on a filter, and also I showed the actual generality of this method with the application of the same controller to a different hydraulic system, which of course in the particular case of the load sensing system, I had to implement another small controller to control the meter out, just to make the system work. So this concludes this presentation, and here is a list of my publications. And before concluding, I would like to thank all the people that helped me over these 4 years, with a special thank to my advisor, which was of great help during my 4 years, was an excellent guy. And a special thank also to Riccardo, Damiano, and Gabriele. We had also an excellent exchange of informations, and also to my committee members, and Anthony Franklin, our lab manager, which always made possible with experimental things. Thank you for your attention.
Okay, so we have an open discussion now before continuing the exam with only the committee members, so we can have questions for Guido or the public. We cannot let Guido.
Okay, I can ask one.
Go ahead.
You had a couple slides where you showed how from the previous method you went from 900 iterations to like 50. When you change the loads on the crane, do you still need these 50 steps, or your gains don't change that much, so you can get away with less iterations?
Yeah, I mean, that's a tough question. For the operating condition I tested, I found that more or less with the same parameters of the extreme seeking, I can reach a similar number of iterations. So, for example, for one operating condition, they might be even 20 iterations. For another operating condition, I might need 70 iterations. But the important, the contribution is that now, instead of using 600 iterations, we can contain the number, which shows the effectiveness of the extreme seeking, which is a pretty fast algorithm.
I mean, and I know that in a crane the dynamics are not going to change that much, but let's say you're extending the arm, your load changes so much. Do you see this working in a real scenario, like in a working scenario?
Yeah, I mean, in your case, in your research, you have to measure this, right?
Yeah.
In this case, as long as you can recognize the operating condition by the pressure and the operator
You just
command.
switch to another one.
If the operating condition is identified, the gain scheduler will pick new parameters and it will work, because those parameters, if they are in the gain scheduler, they have been optimized.
Yeah.
Of course, if you ask me how do you feel about extrapolating parameters from the gain scheduler, that I don't know. I would prefer not to extrapolate, but what I noticed during my experiments is that it's going to a slightly different operating condition, the behavior of the machine using similar parameters is still good. But I mean, this is just a feeling. Of course, there is.
Okay. So you didn't test the transition basically on these operating conditions, or you did? Let's say you have two identified ones.
Yeah.
Okay.
I mean,
So that works fine?
Yeah.
Okay.
As long as the operating condition is identified properly, that works.
Okay.
And probably on a crane it's easier. I mean, I'm not an expert crane operator, but I don't know if they usually swing and also extend the telescopic stages. I don't know.
It depends on the load.
On an excavator, it's more likely because they can swing and also open the boom. But still, it's the same answer. If the operating condition is identifiable,
Identifiable,
it will work.
Okay.
If not,
Then
troubles.
God knows what happens.
Then you have to put a sensor.
All right. Good. Thanks.
Guido, when you have the load swinging, I get in my car.
I mean, actually, I want to take a picture with the crane on top of your car.
Other
So,
questions? Edison?
slide 53, real quick. Maybe not 53. Go back a couple. It was this. Yes, this one. Where it seems like at first your parameters that are being optimized are quite high, 10, 15, 20, and then it seems like it more or less goes to 0, at least in the proportional case. My thought was, does the extreme seeking in this case have enough, I don't know if the term is resolution, or does it go to a low enough accuracy that it really actually meets a good value here, or can you just say that more or less the proportional value went to 0 roughly?
No, I mean, the proportional goes basically like 2.5 or so. The discretization you see here is something I had to, because this is an optimization on the experimental setup. So when you use, in order to have less boundaries in the optimization, I left the parameters range pretty high, pretty large. But when I go with 20 as KB and 10 as KD, the machine really gets dangerous. So what I implemented is there is a button lab where I stop and I generate a cost function number which is big and just proportional to the parameter. So that's why here you see this huge discretization, while here is more, is getting more fine values. So it's not a resolution problem, also just a practical measure I had to use to avoid, to hit the entrance curve.
Yeah, I think that's my only question. Well done.
Okay, so one last question. Well, if not, thanks again, Guido, and you need to leave the room, and we probably